In Chapter 2, we're going to focus on displaying data in a meaningful way. We begin this chapter with a lesson on frequency distributions. Looking at this large list of numbers, it's very difficult to see any trends or any important meaningful characteristics of the data. However, once we organize this data into a table and group it by classes, we can more easily see features of the data. We now know that 23 people are from 19 to 22 years old, and that 17 are from 27 to 30 years old. Organizing data in a meaningful way can help us see the forest for the trees. Let's talk about 5 important characteristics of data. The first one is the center. The center is a representative value that shows where the middle of the data is located. Variation is a measure of the amount that the data values vary. In other words, how spread out are the different data values. Distribution is the nature or shape of the spread of the data over the range of values. One shape that you may have heard of before is bell-shaped, which we also call a normal distribution. Outliers are sample values that lie very far away from the rest of the data. And our last characteristic is any change in the characteristics of the data over time. A dot plot is one way to see the frequency of each data value. Let's create a dot plot for this set of data, and then we'll talk about the center, variation, distribution, and outliers. The first step in creating a dot plot is to draw a horizontal line above all possible data values. Notice that our data set contains the values from 1 to 10, so I'll list out the numbers 1 to 10 underneath a horizontal line. Now we'll go through our list of data values, and we'll place dots above each value 1 through 10, similar to how we might make tally marks. Our first data value is a 1, so I'll place a dot above the 1. The second data value is a 5, so now I'll place a dot above the 5. Next we have a 10, so I'll place a dot above the 10, then a 4, and so on. This is a completed dot plot, and it allows us to see which data values occur with the greatest frequency, or the most often, and it allows us to see other characteristics of the data. Let's first talk about center. If we had first just looked at the list of data values, we may have thought that the center might be around 5 since the data values go from 1 to 10. However, looking at the dot plot, we can see that the center is more likely around 2. In terms of variation, or the spread of the data, we could say that this data ranges from 1 to 10. Now let's talk about the distribution, or nature, or shape of this data. We can say that the data is clustered around the data values 1 and 2, and that there's a gap from 5 to 10. Finally, we can also see that there's definitely an outlier. This single data value of 10 is very far away from the rest of the data. So this is an example of an outlier. Now let's change the conversation and look at a frequency table. While a dot plot can show us some important features of a set of data, it may not be very useful if you have a very large data set. That's where we will focus on a frequency distribution or frequency table. A frequency distribution shows how data are partitioned among several categories or classes. This is what we mean by classes. It's the categories that we create to group different data values together. The lower class limits are the smallest numbers that can belong to each of the different classes. So in this example, the lower class limits are the numbers 15, 19, 23, and 27. In contrast, the upper class limits are the largest numbers that can belong to each of the different classes. So in this example, upper class limit are the values 18, 22, 26, and 30. Class boundaries are the numbers used to separate the classes, but without gaps created by class limits. In other words, we want the centers of the gaps between classes. Take a look at our first two classes. The first one goes from 15 to 18, and the second goes from 19 to 22. Between the numbers 18 and 19, there's a gap. And the class boundary between these two classes is the center of that gap. The center between 18 and 19 can be found by adding them together and dividing by 2. So this class boundary is the number 18.5. We can follow the same process to find all class boundaries. Between the first two classes, we found that the class boundary was 18.5. Between the second two, we want the middle between 22 and 23, or 22.5. Between the third and fourth class, we need the center between 26 and 27, or 26.5. There are two more class boundaries, and we can use the pattern that we've found so far to write those down. The class boundary that comes before the first class is the number 14.5, and the class boundary that comes after the fourth class is the number 30.5. So for this example, our class boundaries are these 5 numbers. Next, we have what's called the class midpoints. These are the values in the middle of the classes. Each midpoint can be found by adding the lower class limit to the upper class limit and dividing that sum by 2. So for the first class, 15 to 18, we find the class midpoint by adding 15 and 18 together and dividing by 2. This is 33 divided by 2, or 16.5. So our first class midpoint is the number 16.5. For our second class, 19 to 22, we can find that class midpoint by adding 19 and 22 and dividing by 2. That's 41 divided by 2, or 20.5. So the second class midpoint is 20.5. Continuing in this way, we can find all 4 class midpoints. Last, we have what's called class width. The class width is the difference between 2 consecutive lower class limits, or 2 lower class boundaries. For example, we could look at the lower class limits for the first 2 categories, 15 and 19. The difference between these 2 consecutive lower class limits is 19 minus 15, or 4. So the class width is 4. Notice that I would get 4 no matter which 2 consecutive lower class limits I chose. If I look at the last 2 classes, I have a difference of 27 minus 23, or 4. Recall that our first 2 lower class boundaries were 14.5 and 18.5. If I looked at these 2 consecutive lower class boundaries, we have a difference of 18.5 minus 14.5, or still 4. So regardless of looking at lower class limits or lower class boundaries, we have the same class width, and this is a consistent difference throughout consecutive classes. Let's try out what we've learned about frequency distributions with an example. For this example, we're going to create a frequency distribution using the following class test scores. Since we are not told exactly how we need to create this frequency distribution, we can choose the classes however we'd like. It appears that this was a test that was out of 100 points, so let's create 5 classes to represent scores from 1 to 100. Our first class could be 1 to 20. And it might be tempting to have the second class be 20 to 40, but then the score of 20 would be in both the first and the second class. So our next class necessarily needs to start at 21. And it needs to be the exact same size as the first class. So this class will go from 21 to 40. One way to double check that you've made these the exact same size is to look at the difference from one lower class limit to the next, a difference of 20, and from the upper class limit to the next, from 20 to 40. Since those are both a difference of 20, these 2 classes are the same size. Our next class will start at 41 and go to 60. The next class will start at 61 and go to 80. And the last class will start at 81 and go up to 100. Now we have 5 classes that are all the exact same size. Now we need to figure out the frequency for each of these classes. That is, how many students have a test score that lands in each of these classes. Let's go through and make tally marks. So for a score of 78, I'll put a tally mark in the 4th class. For a score of 55, I'll put a tally mark in the 3rd class, and so on. Now we have the class frequencies. 3 students have a score from 1 to 20. 1 student scored from 21 to 40. 4 students scored from 41 to 60. 8 students scored from 61 to 80. And 7 students scored from 81 to 100. For a quick double check, let's add up our frequency column. We have a total of 23. The sum total of the frequencies should be the number of test scores that we have in our data set. And we do. There are 23 test scores total. Now that we have our frequency distribution, let's talk about some of its attributes. First, what are the lower class limits? The smallest number that can belong to each of the different classes. In this case, those are the numbers 1, 21, 41, 61, and 81. Our upper class limits are the largest numbers that can belong to each of the different classes. And in this case, that's 20, 40, 60, 80, and 100. Next, let's calculate the class boundaries. Recall that those are the numbers that separate the classes. They are the center of each gap between one class and the next, or before and after the first and last classes. The first class ends at 20, while the second begins at 21. The center of that gap is 20.5. The second class ends at 40, and the third begins at 41. The center of that gap is 40.5. The third class ends at 60, and the fourth begins at 61. The center of that gap is 60.5. The fourth class ends at 80, and the fifth begins at 81. So the center of that gap is 80.5. The only thing we need to add to this list of class boundaries is the first class boundary and the last class boundary. Using our intuition and the pattern that we see here, we can tell that the lower class boundary for the first class is 0.5, 0.5 less than the lower class limit. And the upper class boundary for the fifth class is 100.5, 0.5 greater than the upper class limit. So here are our class boundaries. Now let's figure out our class midpoints. To find the class midpoint for the first class, we add 1 and 20 and divide by 2. That's 21 divided by 2, so the first class midpoint is 10.5. To find the midpoint of the second class, we add 21 and 40 and divide by 2. That's 61 divided by 2, or 30.5. Doing the same calculation for the third class, we have a class midpoint of 50.5. For the fourth class, the midpoint is 70.5, and for the final class, the midpoint is 90.5. Finally, let's calculate the class width. Remember that we can calculate the class width by finding the difference of any two consecutive lower class limits or any two consecutive lower class boundaries. For example, if I look at the two lower class limits, 41 and 61, their difference is the class width. So our class width is 61 minus 41, or 20. And we would find the same class width no matter which two consecutive lower class limits or boundaries we chose to use. A variation of the basic frequency distribution is the relative frequency distribution. This is where we take each class frequency and we replace it by a relative frequency, or proportion, or a percentage. To calculate the relative frequency for a class, we need to take the frequency for that class and divide that by the sum of all the frequencies. For example, let's look at the same data set that we just created our frequency distribution for. Here's our frequency distribution with a total frequency of 23. To turn this into a relative frequency distribution, we still have the same classes, but in place of frequency, we have relative frequency. And for each class, we can calculate the relative frequency by taking the frequency and dividing it by the total frequency, 23. So for the first class, we'll take the frequency of 3 and divide it by 23. As a proportion, this is 0.1304. And as a percentage, this would be 13.04%. For the second class, we take the frequency of 1 and divide it by the total of the frequencies, 23. Putting this into our calculators, we have a proportion 0.0435. And written as a percentage, this is 4.35%. For the third class, we'll take our frequency of 4 and divide it by 23 to get the proportion of 0.1739, which as a percentage is 17.39%. For the fourth class, we take the frequency of 8 divided by 23, and we have the proportion 0.3478, or the corresponding percentage 34.78%. And finally, for the last class, we take our frequency of 7 and divide it by 23 to get the proportion of 0.3043, which is the equivalent of 30.43%. Now we have our relative frequency distribution. If we add up all of our relative frequencies, we should get a number that's very close to 1. If we're off by a tiny bit, that's okay because we did have to round to get these proportions. Adding up percentages, we expect to get a number that is very close to 100%. There is one more type of frequency distribution that we need to discuss, and that's our cumulative frequency distribution. This is another variation in which the frequency for each class is the sum of the frequencies for that class and all previous classes. In other words, we're going to keep a running total as we go from one class to the next. Let's take a look at our frequency distribution that we already created. In order to create the corresponding cumulative frequency distribution, we do need to change our classes. For our first class, instead of writing 1 to 20, we will use a different language. We will write less than 21. It might be tempting to write less than 20, but then the score of 20 is no longer in that first class. So we'll write it as less than the next class. And since there are 3 students that scored less than 21, our cumulative frequency for the first class is 3. For the second class, instead of only wanting the scores from 21 to 40, we want the frequency from the second class and the one before. So we will write this as less than 41. Notice that that encompasses the first 2 classes from our frequency distribution. So we have a total of 4 students that scored less than 41, and our cumulative frequency is 4. Next, we want all scores that are less than 61. This will include the first 3 classes from our frequency distribution, and we have a cumulative frequency of 8. Next, we want all scores that are less than 81, which will include all of the first 4 classes, for a sum total of 16. And finally, to include all 5 classes, we will write less than 101. And adding up all 5 classes from our frequency distribution, we have a sum total of 23. Notice that our last cumulative frequency is the sum total of the frequencies. If it's not, then you likely made a mistake somewhere along the way. The last thing that we'll talk about in this lesson is the idea of a normal distribution. Data that have an approximately normal distribution are characterized by a frequency distribution with the following features. The frequencies start low, increase to 1 or 2 high frequencies, and then decrease back to a low frequency. In addition, the distribution is approximately symmetrical. Those that precede the max roughly mirror those that come after. Let's take a look at a couple of pictures. In this first bar graph, notice how the frequencies start small, increase to 1 or 2 maximum values, and then return back down to lower frequencies. That's an approximately normal distribution. It approximately takes on the shape of a bell curve. In terms of a frequency distribution, we start with some lower frequencies, we increase to a few higher frequencies, and then we return back down to a few lower frequencies. This again is an approximately normal distribution. If a distribution is exactly normal, that means it's an exact bell curve, and the frequencies exactly mirror one another on either side of the maximum frequency. Notice that if we take this first frequency and change it to 1, now our frequencies exactly mirror one another on either side of the highest frequency, and this would be an exactly normal distribution. Let's think about why we should look at frequency distributions and the type of information that they give us. Looking at this first frequency distribution for the weight of pennies in grams, what do you notice? There is a large gap in the data. It seems that there are pennies that weigh between 2.4 grams and 2.59 grams, and other pennies that weigh more than 2.9 grams, but nothing in between. This lets us know that this data set was quite possibly collected from two populations. Before 1982, pennies were made mostly out of copper. But after 1982, that changed quite dramatically. That makes sense out of this gap in the data. There are two different populations of pennies going on. Now let's take a look at this second table. What we have here is two relative frequency distributions put side by side, which allows us to compare two sets of data. It's important that when we compare two sets of data that we use a relative frequency distribution. That way we are comparing apples to apples with percentages or proportions rather than simply raw data that may or may not be comparable. But with this comparison with relative frequency distributions, we can clearly see that Dunkin' Donuts has quicker service times than McDonald's. That concludes this lesson on frequency distributions. Hopefully you gained an understanding of what a frequency distribution is and how it can be used to display data in a meaningful way.